Hello and welcome to this lecture. So we've been looking at inner products and how it plays a role in giving a sense of angle and norm and how it can be used to find least square solutions to a set of linear equations and all of that. Another very interesting use for inner products and inner product spaces is this notion of adjoint of an operator. And once you have adjoint of an operator and how the adjoint and the operator are related, end up giving us a lot of ideas on how operators work, in particular how eigenvalues and eigenvectors of operators work. So we're going to take the next important step and study this notion of an adjoint of an operator in general. We already saw it in R2. This is a more general definition and understanding of adjoint. Another closely related idea is this Hermitian of a matrix, and both of these will be introduced in this lecture. Okay, so the first thing I want to start before first thing I want to say before starting on this is, from now on we'll only use orthonormal basis. Okay, so a lot of things I say will be true only when we use an orthonormal basis and not for an arbitrary basis. This notion of the Hermitian, particularly for a matrix, works only with orthonormal basis. So from now on, mostly we'll stick to orthonormal basis. Okay, so here's the definition. We again always start with this linear transformation T, which goes in general now from Cn to Cm. It's a linear transformation now. I'm not talking about an operator. In general, a linear transformation T that goes from the n-dimensional complex space to the m-dimensional complex space. Clearly, it's going to be represented by an m cross n matrix A with respect to some orthonormal basis. It could be the canonical basis, but an orthonormal basis is good enough. Okay, so this is how it looks. This is A, m cross n, a11 to a1n in first row, and then am1 to amn is the last row. Okay, so first thing I want to define is something called the Hermitian of this matrix. So you have this matrix. The Hermitian is nothing but conjugate and transpose. So we've seen transpose. Transpose is the first row will become the first column and so on. The rows and columns are interchanged. So that's transpose. And then there's the operation of conjugate, because these are all complex numbers. These Aij are complex. You can also conjugate them. So how do you find A Hermitian given A? You do the transpose and then you conjugate everything. So this A Hermitian will be an n cross m matrix. When A is m cross n, it will be n cross m. Okay, and all the entries are conjugated. Okay, so that's how the A Hermitian works. You can take a small example and then write it down. You'll see how Hermitian works. It's basically conjugate transpose. Okay, what is adjoint of the operator T? So this is how I'm going to define it like this. It's sort of like a shorthand way of defining it. There are better ways of defining adjoint, but we will use this simple definition for our purposes in this class. Okay, the adjoint of T, which we will denote as T star, basically is the linear transformation from Cm to Cn, and it's represented by A Hermitian. Okay, so that's the big definition here. So from the matrix A, we go to the matrix A Hermitian, and then we define the operator itself through this A Hermitian. We say the operator that is represented by A Hermitian is the adjoint of the operator T. Okay, so clearly T and T star are very closely related. A and A Hermitian are very closely related. So the linear transformations they represent are also going to be very closely related, and their properties sort of are tied together in very interesting ways, which is what we'll see. But as definitions go, it's a very simple definition. You start with an operator, look at its matrix with respect to an orthonormal basis. That's very important. And then you go to the Hermitian of the matrix, and then go to the operator that is represented by that. Again, the orthonormal basis is always kept the same, and that's very important. So A is with respect to an orthonormal basis, and A Hermitian is with respect to the same basis. We define the operator T star. Okay, so this is the definition for adjoint and Hermitian. At this point, it may not be clear to you why this is such an important definition and why it plays a role in eigenvalues and all that. We'll see a few results which will give you an idea, and then later on when we study the spectral theorems, you'll see how powerful this notion of an adjoint is. Okay, so let's get started. Okay, so the first and important connection between Hermitian, adjoint and inner product is this following connection. Okay, so this connection is at the heart of many of the ideas involving Hermitian and inner product. So this Hermitian adjoint and inner product are are closely connected, and we are going to see that connection. Okay. So, once again, let us start with the linear transformation T, which goes from Cn to Cm. It is represented by an m cross n matrix A, and we already saw that the adjoint T star is from Cm to Cn, and it is represented by an n cross m matrix A Hermitian, again orthonormal basis, keep that in mind. So, we can draw a picture like this, right. So, a picture like this is maybe sort of illustrates what is going on. You have Cn here represented by this ellipse, and then Cm is represented by this ellipse. If you have a vector u in Cn, you do Au, you go to Cm, and that is T of u, right. So, T of u is Au, and that goes to Cm. Okay. Likewise, you can start with a vector v in Cm, and then operate it with A Hermitian. So, you multiply with A Hermitian v will take you to Cn, and that is my T star of v. Okay. So, from Cn you can go to Cm, and from Cm you can go to Cn, and that is the definition for T and T star. Okay. So, notice this very interesting relationship. If you look at the inner product of T of u and v in Cm, right. So, notice what is going on here. So, ultimately it turns out, if you look at the inner product of T of u and v in Cm, it is the same as the inner product of u and T star of v in Cn. Okay. So, notice how this is working out. I have two vectors here in Cm, T of u and v. I can take an inner product here, and I have two vectors here, u and T star of v. I can take an inner product here. I am doing inner product in Cm here, inner product in Cn here, and guess what? By the definition of T and T star, these two inner products are exactly the same. Okay. So, that is the crucial property that connects everything. In fact, this is one of the defining properties of the adjoint. I am sort of defining, I am sort of deriving it in some way, but it is the defining property for the adjoint. Okay. So, the way it works is quite simple. You can see T of u comma v is v Hermitian Au, right. So, that is the definition with the matrix representation. Now, notice here this v Hermitian A is matrix product is associative. So, I can bracket these two together and use separately, and then this v Hermitian A I can identify as A Hermitian v whole Hermitian. Okay. So, that is the subtle little trick here. It is no big deal in one level, but you can see how the Hermitian sort of enters the picture. V Hermitian A is the same as A Hermitian v, the whole thing Hermitian. Okay. So, this is a very crucial property, and once we see this, everything else works out. So, from here you notice that this is nothing but the inner product between u and T star of v, right. So, notice how the inner product between T of u and v becomes inner product of u and T star of v, and this is a defining property of the adjoint of an operator. Okay. So, these two inner products are exactly the same. So, this has a lot of connections to how eigenvalues work, how spectrum works, and all of these things. Okay. So, we will see that as we go along. Okay. So, a whole bunch of properties. I already used some of these properties in the previous one when I looked at Hermitian and all that. I'll just list it down properly in a sequence. The first is sum. Okay. If you have two operators, you add them and then take adjoint is the same as adding the adjoints. The matrices in the matrix world is quite easy to see. A plus B Hermitian is A Hermitian plus B Hermitian. And then scaling is a very interesting property. If you have a complex number lambda, you multiply an operator with lambda and then take adjoint. It's the same as doing lambda bar times T star. Again, from the matrix point of view, it's quite easy to see lambda A Hermitian. You can take the lambda out and have a lambda bar there and multiply A Hermitian. It's quite easy to see. Product is a little bit tricky. I used the product property in the previous derivation. So, if you have AB, multiplying AB and taking Hermitian is the same as B Hermitian, A Hermitian. Okay, the order changes. Even in transpose, the same thing happens. So, in Hermitian also the same thing happens. It's the other way around. And the same thing in terms of operator language. You can see S composed with T adjoint is the same as T adjoint composed with S adjoint. Okay, so this is the product property. And then repeated adjoint. If you do T star star, adjoint of the adjoint becomes the operator itself, right? So, you can go back to that inner product picture and you will see that's very easy to see. And in the matrix world also, you do A Hermitian, then Hermitian again, you are going to conjugate again and then reverse the row and column, you are going to get the same thing. Okay. So, these are all properties that make algebra with adjoint and Hermitian easy to do. So, if you now have, we saw a lot of matrix algebra multiplication, and now if you have Hermitian thrown in, you know how to do algebra with the Hermitian thrown. Okay. So, that is something very simple and interesting to see. Okay. A few more simple things. So for the identity operator, I star is I, right? So that joint is itself. And if you have a matrix with real entries, this is also an important property, sometimes it shows up. If you have a matrix with real entries, then A transpose is the same as A Hermitian. You don't have to bother with the conjugate, Hermitian becomes the transpose. Okay. So this is a quick collection of properties. They're quite easy to prove. There is nothing majorly difficult here. I am not going to show the proof in detail, but you can use these in a lot of algebra. Even in the previous derivation of the inner product, we used the product rule here. Okay. So that's properties for the adjoint and the Hermitian. Okay. Another interesting connection is in the fundamental spaces. So we saw that every linear transformation has 4 fundamental spaces associated with it. Now when you look at A and A Hermitian, there are connections between these fundamental spaces, and these connections are quite easy to derive. I'm not going into great detail, I'll simply present the final result for you. Okay. So if you start with the matrix A, you know that the range of the transformation is the same as I put equal to here. You know what it means, it's sort of the same. The column space of A, null space of T is the null space of A, and we know that the rank of A is column rank, row rank, all of these are same. Nullity of A is n minus rank of A. So we know that this is true. Dimension of null T is nullity, it's n minus rank of A. Now if you go to A Hermitian, you can write down the same things here, but then you notice that the column space of A Hermitian is the row space of A, the whole conjugate. Okay, so you do the row space of A and then simply conjugate every entry wise, you're going to get the column space of A Hermitian. Same thing with null space of A Hermitian. Null space of A Hermitian is the left null space of A, but then you have to conjugate the whole thing. Okay, so these are two interesting connections between the fundamental spaces of A and A Hermitian. So once you see this, you see from the first relationship, it's immediately clear that rank of A Hermitian is the same as rank of A. Okay, that's also easy to see. Row rank, column rank, all of these are the same. And then nullity of A Hermitian is going to be m minus rank of A, right? So it's m. So this n and m are different here when you look at linear transformations in general. Okay, so this is n and this is m. Other than that, the ranges have the same dimension. So rank is the same. Rank of A and rank of A Hermitian are exactly the same. So these are not difficult things to prove. We know that the row rank and the row rank and the column rank are the same. The only thing that's going on is conjugation. That doesn't change anything fundamentally. So you get the same rank. Okay. So that's fundamental spaces of linear transformations. Once again, I think this orthonormal basis is something that will stick with us. I'm just putting it out there so we don't miss it. Okay. So what about operators? When you go to operators, in fact, everything becomes the same because this m and n are not different anymore. Operators are square matrices n cross n. So you just have the same thing. You know, the rank of A is the same as rank of A Hermitian. Nullity of A is also the same as nullity of A Hermitian when you have a operator. When A is representing an operator and A is a square matrix. Okay, that's quite easy and reasonable to see. Okay. Another thing about eigenvectors and eigenvalues for A and A Hermitian. If you have an operator T represented by A, okay, the eigenvector usually operates on the right, isn't it? So if you multiply AV equals lambda V is the eigenvector equation. So you solve for it, lambda becomes the eigenvalue. So it's multiplying on the right, right? The vector V multiplies on the right and you have an equation like this, okay? But you can also multiply on the left with a row vector, right? Not a column vector, but you can multiply A on the left with a row vector. But how does that work? So that has a connection to T star. Now we know operator T star is represented by A Hermitian, which is the Hermitian of this matrix here. Now if you think of an eigenvalue vector of T star, you're going to multiply on the right again, right? So A Hermitian W equals mu W is a eigenvector for A Hermitian. Okay, so you get an equation like this. This equation is nice enough, but then I can take Hermitian on both sides. Okay, so if you take Hermitian on both sides here, I'm going to get W Hermitian times A equals mu bar, the conjugate of mu, times W Hermitian. So you notice here that this is a row vector multiplying A on the left, okay, and then you get some constant value mu bar, which is like the eigenvalue multiplying the same vector directly. Okay, so this is like a sort of an equivalent eigenvector eigenvalue equation, except multiplication on the right is replaced by multiplication on the left. So you don't have right eigenvectors, you have left eigenvectors. Okay, so an eigenvalue eigenvector of T star or A Hermitian becomes actually the left eigenvector for A. Okay, So this is an important and subtle point. It's quite simple to look at it at some level, but hopefully you see what's going on here. So when you think of eigenvalues and eigenvectors of A Hermitian, those are actually the left eigenvalues and left eigenvectors of A. Okay, so you can just keep A itself and then think of the left and right eigenvalues, and you would be doing eigenvalues and eigenvectors for A Hermitian. Okay, so that's one other connection and definition that plays an important role. Okay. Finally, here is a very, very nice property that connects the eigenvalues of an operator and its adjoint. Okay. If you have an eigenvalue lambda for an operator T, then the conjugate of lambda, which is lambda bar, becomes an eigenvalue for the adjoint T star. Okay. So if you have an eigenvalue for the matrix A, and if you look at A Hermitian, then lambda bar is an eigenvalue for that. The proof is actually very, very simple. Lambda is an eigenvalue of A, so A minus lambda is singular. Okay. Now, if I take Hermitian, the rank doesn't change, isn't it? So, rank of A and rank of a matrix and its Hermitian are the same. So, A minus lambda is singular means it's not full rank. So, A minus lambda I Hermitian will also not be full rank. So, it will be singular. So, A Hermitian minus lambda bar I is singular. Okay. So, this Hermitian goes in, you use the sum rule and the scaling rule and all of those things. You see, you get A Hermitian minus lambda bar I is singular, and so lambda bar becomes an eigenvalue of A Hermitian. It's a very, very simple proof. You can also write it in operator language. I have written it in the matrix language here. Okay. So, this is a very, very important property, and this sort of concludes this quick definition for adjoint and Hermitian. These things are going to play a very, very important role now, and you see how inner product combines with the definition of the operator through this adjoint definition. Okay. So, when you think of the inner product, how to do inner products with the linear transformation, there are two ways of doing it, and they are related through the adjoint, and this is how the inner product enters the world of linear transformation. So far we have been studying linear transformations without inner products. We studied eigenvalue and all of that without inner products. Now when the inner product comes in and the adjoint comes in, the whole study of eigenvalue, eigenvectors become really, really important, and we can ask a lot of very interesting questions, and that's what we will do in the rest of the topics. Thank you very much.